What's up, everybody? Here is the integration by parts handout, and let me just remind you what integration by parts says. Basically, if we have the integral of a product of two functions where we identify one as u and the other one as a derivative of some function v, this can be rewritten as u times v minus the integral of u prime v. So what does that tell us? That tells us that we start with some integral that we are trying to solve, and we end up with a different integral where the derivative of u shows up and the antiderivative of v shows up. So that means that we have to choose the u such that this derivative becomes simpler, and the v prime, we choose it in such a way that we know the antiderivative. So let's do the very basic example for integration by parts, integral of the function x times e to the x. Over here, notice that the x part, when I take derivative, it becomes simpler. So that means I should choose u to be x so that u prime is just 1. And also the other component here, e to the x, I know it's antiderivative, so that means that this should play the role of v prime, which makes v e to the x also. So that means what? That means that this integral is equal to now u times v, so x e to the x, minus the integral of u prime, which is 1, times v, so times e to the x again with respect to x. So that should be x e to the x minus integral of e to the x is just e to the x plus c, and that is our final answer. Let's move on to the next problem. This time I'm multiplying x by sine of x, and again I should choose the u to be x because its derivative becomes simpler, and sine of x, I know it's antiderivative, so that's going to make things easy. So let's go ahead and let u equals x, u prime is 1, v prime is sine of x, and the integral of that is negative cosine, so v is negative cosine of x. And let's go ahead and run through the formula for integration by parts and plug everything in. So this should then be the not the integral, should be u times v, so x times minus cosine of x, so I'll just write it as negative x cosine of x, minus now the integral of u prime times v, so 1 times negative cosine of x. So we're going to pick up an extra minus sign, which means I might as well make this a plus integral of cosine with respect to x. And now let's go ahead and integrate this second integral. So I have negative x cosine x, that's the first part, I just copied down, plus integral of cosine is sine, plus c. That is the second problem. Now, sometimes when we do integration by parts, the integral that we end up with requires us to repeat the process one more time, and this is a very good example of that. Again, I'm going to choose the u to be x squared so that the derivative u prime is just 2x. Then the v prime is going to be e to the minus x, and the antiderivative of that is negative e to the minus x. And if I plug in into the integration by parts formula once, I get these two multiplied, so negative x squared e to the minus x minus the integral now u prime times v. So I pick up an extra minus sign, so I'm going to make this a plus 2x e to the minus x. And now the second integral needs integration by parts one more time. So I'm gonna let this time the 2x to be the u, so let me write it here. U is 2x, the v prime is e to the minus x again, for the same reason as before. U prime is 2, and v is negative e to the minus x. So let's apply that. So that means that this integral now is equal to, okay, first part I just copy it down, minus x squared e to the negative x, plus, now I have u times v, so actually I'm going to make that a minus 2x e to the negative x, and then minus now the integral of u prime v, so 2 times negative e to the minus x. And since this is negative and I have a minus sign there, I'll make this a plus integral of 2 e to the negative x with respect to x. And now we can finally integrate that last piece. So the final answer should be minus x squared e to the negative x minus 2x e to the negative x. And finally I have minus 2 e to the negative x. The minus comes from integrating e to the minus x, so we pick up an extra negative sign, plus c, and we are done. So these are three very basic examples of integration by parts, and it's quite simple, right? So you choose a function for u such that the derivative in general most of the time will become simpler, and similarly you do the same for the v prime, right? You choose it so that you know its antiderivative. Let's do some more examples. And over here I have some examples where it's not at all obvious what the u or the v should be. In fact, we don't really have a product of two functions here, so we have to artificially create that. So how am I going to do this? Well, I'm going to write ln x as 1 times ln x with respect to x. And now I go through the process, right? I have to choose the u, I have to choose the v prime, u prime, and v. If I choose the u to be 0, and this to be the v prime, the ln x, I need to come up with the v, and that's basically asking the original problem, right? So that's not going to help us because we don't know what the antiderivative of ln x is, so I can't come up with the v. So then I'm going to do it the other way around. I'm going to let u be natural log x, so that u prime is 1 over x. V prime, I'm going to let it be 1, so that the antiderivative of that is just x. Let's see what happens. So let's plug it into the integration by parts formula. I have u times v, so I have x times natural log x, minus the integral of u prime v, so I have 1 over x times x was our v. And notice that here things cancel, so all I'm integrating is 1, which means the final answer is x natural log x minus integral of 1 is x plus c. And here's another example where the same thing happens, right? You're integrating a function, you have to rewrite the integral as 1 times arctan of x, so that this will enable us to use integration by parts. And for the same reason as before, I'll let the u be arctan. That I can't let v prime be arctan because I don't know what v would be in that case, right? I don't know the antiderivative of arctan. So the v prime has to be the 1. U prime is then derivative of arctangent, so that's 1 over 1 plus x squared. And v is the integral of 1, which is just x. So what does that mean? That means that this integral now becomes u times v, so x times arctan of x, minus u prime v. So minus the integral of u prime v, so I have x on top 1 plus x squared dx. Now this integral we can do by substitution very easily, where you let the bottom piece be u. But if you've done substitution enough times, you know that the antiderivative here would be a natural log of 1 plus x squared. But if I take the derivative here, I end up with 2x on top, so I need to divide by that 2, so that I actually get just a single x on top, add my c, and you are done. Okay, so here were two examples where we didn't necessarily have a product of two functions, but we artificially turned it into a product of two functions, the constant function 1, a natural log in the first case, and here 1 times arctan for the second case. So now, problem 6. Up until now, I've been telling you guys to choose the u so that the derivative becomes simpler. You choose the v so that the antiderivative, well, you know it. But in this particular case, none of those things applies, right? So what would you choose the u to be? What would you choose the v to be? And you have to try a couple of things, right? So the first thing I'm going to try is to let u be e to the x, and to let v prime be sine of x. That makes my u prime equal to e to the x, and that makes my v equal to negative cosine of x. And let's see what we get if we do it this way. We're gonna have u times v, so we're gonna have negative e to the x cosine of x, and then we're gonna subtract the integral of u prime v. And since v already has a minus sign, I'm gonna make this a positive, and then I'm integrating e to the x cosine of x with respect to x. Okay, so far so good, but that doesn't help us because we are back to an integral of the same form as the one we started, except now the sine is replaced by a cosine. But let's see what happens if we repeat this process one more time. So again, I'm going to let u be e to the x, so u prime is again e to the x. I'm going to let the v prime now be this cosine function, and v be, well, the antiderivative of cosine is just sine, and that gives us, if we apply integration by parts one more time, I'm just going to copy this part down, minus e to the x cosine of x, and now this integral becomes u times v, so plus e to the x sine of x, minus the integral of u prime times v, so e to the x sine of x dx. So what did we just do? We did integration by parts 2 times, and we ended up with an integral that looks exactly, that's exactly equal to our starting integral. In other words, we have the following equality. We have whatever we started with, integral e to the x sine of x with respect to x, and we showed that this is equal to, let me factor out e to the x from here, and I just have sine of x minus cosine of x once I factor that out. The cosine is the negative one, and then again I have minus the integral that I started with, e to the x sine of x dx. So it seems like I'm stuck, but what I can actually do in this case is I can take this integral here, move it on the left hand side of the equation, right? So that means I get 2 copies of that, and this disappears from here. And how do I solve for this integral? It's easy, I just divide by 2. So that tells me that the integral of e to the x sine of x with respect to x is 1/2 e to the x sine of x minus cosine of x, and plus c because we have to account for the constant of integration. This is an indefinite integral. Okay, so that was one example where we appear to be stuck, but actually if we do some manipulation after applying integration by parts a number of times, we can actually solve for the original integral. Let's also look at number 7, right, which is asking us to prove the reduction formula, where if I integrate the nth power of natural log, I get this expression right here. Okay, well, let me start with the integral of ln of x to the power n with respect to x, and I'm going to try to apply the same technique that I did when I was just integrating natural log alone. In other words, I'm going to add an extra 1 times the function here, and then I'll let the u be the natural log part, and I'm going to let the v prime be the 1. Well, that means that u prime is going to be, and here I just apply chain rule, so it's what do I have? N natural log of x to the power n minus 1, which is good because in the answer this to the power n minus 1 appears, right? So that's a good sign, times the derivative of natural log, which is 1 over x, and the v is going to be the integral of 1, which is just x. So let's go ahead and try to apply integration by parts now, and plug it in and multiply things as we should. So I get x times natural log to the n minus the integral of u prime times v. So u prime, I'm just going to copy it. It's n times ln x to the power n minus 1 times 1 over x, and the v is x, so I multiply it there with respect to x. And so now notice what happens. The x's cancel, n is just a constant, so I might as well bring it in front of the integral, and this is exactly the result that we were trying to prove, right? I have x times ln x to the n here, and then I have n times the integral of ln x to the n minus 1. So it does indeed show that this formula is correct. I have just a couple more problems, right? So we've already seen the integral of e to the x, x e to the x, and we've also seen the integral of x squared e to the x. In the first case, we just had to apply integration by parts 1 time. In the second case, we had to apply it 2 times, so that was a little more annoying. But what if I put x to the 4th? That would mean I would have to do integration by parts 4 times. And that's a lot of work, right? It's a lot of writing. In fact, if I were to do it, I probably wouldn't be able to fit it all into this space here. So I'm going to teach you guys a shortcut for when you have to repeatedly apply integration by parts, and that's something called tabular integration. And I actually looked at the textbook, and that's where I actually got a lot of these examples, and they don't talk about it there, which kind of surprised me, but I want to show you guys how to do this. And basically you start by building a table with 2 columns. Over here we're going to put the letter D, which stands for differentiate, and over here we're going to put the letter I, which stands for integrate. And if I'm looking at the integral of x to the 4th e to the x, I have to choose a function that I'm going to differentiate, and I have to choose one of these that I'm going to integrate. So And again, just like when we do regular integration by parts, I choose the function that I differentiate, which is always the u, so that the derivative becomes simpler. So I'm gonna put then x to the fourth over here, and I'm gonna put e to the x over there. Now what I do is I go down one row, and as I go down in this column I take derivatives, in this column I take integrals. So let's see, I differentiate x to the 4, that's 4x cubed, integral of e to the x is e to the x. Let's do it one more time. So derivative here is now 12x squared, integral here is e to the x. One more time, then I end up with 24x, integral is e to the x. One more time, I end up with 24, integral is e to the x. And when I take one more derivative, I finally end up with 0. I take one more integral, I end up with e to the x, and that's where I stop. Now I have this table, right, where on one column I was taking derivatives, on the other column I was taking integrals. And what I'm going to do is I'm going to go from the top element just diagonally down one row, just like so. Then I'm going to assign signs to these arrows that I drew. The first one is always a plus. Then I put a minus, then a plus, then a minus, then a plus, just like so. And now I'm ready to give you the answer in 20 seconds, right? And the answer is this. The integral of x to the fourth e to the x is x to the fourth times positive e to the x, so times e to the x. Next one has a negative sign. I multiply these two, so minus 4x cubed e to the x. I go one more down, plus 12x squared e to the x. I go one more down, minus 24x e to the x. And the last term is plus 24 e to the x. I add my plus c. This is the answer after you apply integration by parts 4 times for this problem. So this technique is called tabular integration, and it helps you find answers basically a lot easier than you would normally. Let's do another example of that to show you how it works if there's sign changes over here, right? So again, I have the integral of x to the fifth now, cosine of 2x. And I just draw my table first. In one column I differentiate, in another one I integrate. The one I'm going to differentiate is x to the fifth. So let me just go ahead and take all the derivatives. 5x to the fourth, 20x cubed, 60x squared, 120x, and the last one is 120 and 0. So those are all the derivatives, and I stop when I reach 0 on the d side. And the function that I integrate is the other one, which is the cosine of 2x. Integral of that, well, integral of cosine is sine, but is multiplied by a half. Then the integral of that is negative 1/4 cosine of 2x, and the integral of that is negative 1/8 sine of 2x. The integral of that is negative 1/16 cosine of, actually no, integral of sine. So now I'm gonna make this positive, not negative, my bad. And the integral of that is 1/32 sine of 2x, and the last one is negative 1/64 cosine of 2x, and I stop because I'm in the same row where the 0 for the derivative side was. So now let's draw the arrows as I did in the previous example. Give me just a second here, I'm out of lead. Okay. I always start with the plus, then minus, then plus, then minus, then plus, and the last one is a minus. And now I can give you the answer just by looking at this table. The first term is x to the fifth times 1/2 sine of 2x. Then the next term has a minus here, but the term here is negative, so that actually is a plus again. 5x to the fourth over 4 from here, cosine of 2x. Then the next term, plus here, but that's negative, so it's actually going to be a negative, right? I just multiply these two things. 20x cubed over 8. The 8 coming from the denominator here, sine of 2x. Then the next term is going to be negative 60x squared divided by 16, because that's their cosine of 2x. Next term, this is positive, right, because there's no minus sign to make a negative, so plus 120x divided by 32 sine of 2x. And the last term is also positive because I have two negatives which multiplied give us a plus. So that's going to be plus 120 divided by 64 cosine of 2x. And finally I write the plus c. That is the answer. So imagine having to do integration by parts 5 times on this problem to obtain this answer right here. It would take a full page of work at the very least. So this method is much easier, right? And you automatically, just after you build this table with the columns and you draw your arrows, you can automatically give the answer. It takes a few minutes. And for the last problem, okay, there's no way for you guys to tell that this is the correct answer, so what I want to do is actually verify the previous results, x e to the x and x squared e to the minus x. When I integrate these, I want to do it with tabular integration. So let's do it here. Integral of x e to the x, and we're going to compare then. Here's the d side, here's the I side. I'm going to differentiate x, I'm going to integrate e to the x. Derivative is 1, then it's 0. Integral is just e to the x all along. I draw the arrows, there's only 2 this time. First one is a plus, second one is a minus. So the antiderivative here should be x e to the x minus now e to the x plus c. And if you go back to the first problem for integration by parts, that is exactly what we obtained doing it the long way. Let's check the second one, right? So I have integral of x squared e to the minus x with respect to x. I draw the table. Here's the function that I differentiate. Here's the function that I integrate. I start with x squared e to the minus x. Take derivative 2x, 2, and finally 0. That's where we stop. Integral negative e to the negative x. Integral again Now it's positive e to the negative x. And integral again makes it negative. Draw the arrows. Plus, minus, and plus, right? So I always start with the plus for the first arrow, then I alternate. But when I multiply these two, even though that's a plus, this is negative. So the first term is negative x squared e to the minus x. Then the second one is minus 2x e to the minus x. And the third one is also negative due to this here. So it is 2 minus 2 e to the negative x plus c. So this is the answer that this tabular integration method gives us. So let's just go back to the example and see if it matches. And it is exactly what we got before, right? Using the long way where we had to do integration by parts 2 times. So notice how much quicker this method of tabular integration is, right? If you had to do it 5, 6, 7 times, you just get a longer table and your answer gets longer. But in terms of difficulty, it's not too difficult to do, right? And it also saves you a lot of time. So I hope you guys enjoyed this method and use it to save time on an exam or a quiz or something like that. And I wish you all good luck.